Hi everyone, this is the third lesson in Waves for Physics A-Level. This is Young's Fringes and Diffraction Grating. This video will cover the Young's double slit experiment and the calculations associated with it, and also how to use a diffraction grating to find the wavelength of light and calculations with the formula shown here. The context of this would be spectroscopy. There's lots of different types, but just focusing in on optical spectroscopy. This is used for a whole range of things, including analysing light from stars in order to work out what elements are inside the stars, and also analysing chemical samples. So what are Young's fringes? So hopefully you will have seen a demonstration of this in your physics lesson, or just find a YouTube video and that might illustrate the details in a bit more depth. But effectively, if you shine a laser light at a single slit, then you'll get diffraction and you'll get a spreading out of the laser light. Now it's a little bit more complex than that, but effectively it's smeared, it's spread out. However, if you shine the laser light at a double slit, then we get diffraction through each of these gaps, and we have two wave sources, coherent sources, spreading out and interacting constructively and destructively. And what we get is what's called a fringe pattern. So we have a bright spot in the middle, and then spots on either side getting slightly fainter as you get further away from the center. So these spots are called fringes, and the fringe spacing is the distance between the center of one dot and the center of an adjacent dot. So why do we get these fringes? So what I've got here is a diagram, slit 1, slit 2, and obviously we only get one color of light, but I've changed the colors here just to separate them and make it a bit clearer. So at point A we get a bright fringe. If you imagine this diffracted ray from slit 1 and slit 2, they both have traveled the same distance to meet in the middle at point A. So the path difference is 0, so the two waves are in phase with each other, so we get constructive interference and we get a large intensity, which is a bright spot. Just to the side of that we get a dark fringe. So we can see that the ray from slit 1 has traveled slightly further than the ray from slit 2. The path difference here is half a wavelength, so they meet in antiphase, or 180 degrees phase difference. So we get destructive interference and we cancel out the light, so we get a dark fringe, an absence of light. And we could continue. So in point C here we get another bright fringe. So here we have ray 1 has travelled a full wavelength further in distance than the ray from slit 2. So now the path difference is a full wavelength, so we have the waves meeting in phase, so we have constructive interference, and so on. So we can use this, as we will see, to calculate a value of the wavelength of light. It's also used as evidence for the wave nature of light, because we have diffraction and superposition interference. And you might think, well, we know that light behaves as a wave, but as we'll see later on in the course, we can also see light behaving as particles when we look at quantum topic and photons of light. So we have the Young's fringe formula. This is one version. Different exam boards will have slightly different symbols. Sometimes we use X instead of Y, but we have lambda, which is the wavelength. It's equal to the separation of the slits, that's the distance between the center of slit 1 and slit 2, multiplied by delta Y, or just Y, which is the fringe separation, so the center of one fringe to the center of an adjacent fringe, divided by capital D, which is the distance between the slit and the screen. So we're given this in the formula booklet, and we need to be able to calculate the wavelength of light, and typically you'll be given, or you can set the slit to screen distance. The distance between the two slits will be given in the slit that you use, and then what we typically do is measure with a ruler the separation between fringes, or more normally you would measure maybe 5 or possibly 10 fringes if they're visible, and then divide by the total. That would be a better way to measure the fringe separation. So let's look at a worked example. So find the wavelength of light in meters. You might be asked in nanometers. We're given the fringe spacing, we're given the slit to screen distance and the slit separation. Okay, so what we need to do is to use the formula. So as we've seen here, A times delta Y divided by D. So A is my slit separation, 1 times 10 to the minus 3. times by the fringe spacing, 0.2, 10 to the minus 2 centimeters, divided by 3.3, and we get an answer of the wavelength of light. So just with relatively straightforward equipment, we can get a very precise calculation or value of the wavelength of light. So this is a remarkable experiment in order to measure the wavelength of light. And we do need to know nanometers, so you can use the ENG button on your calculator to convert this into nanometers. And the significance of this is the approximate wavelength of red light. So you are expected to know the wavelength of violet light, which is 400 nanometers, and the other end is the wavelength of red light, 700. So these are the two extremes. So I had to have a rough idea of 6 10 to the minus 7 or 610 nanometers is going to be round about here. So it's approximately red, which in this case is normally the color of light we would use for a laser in the Young's fringe experiment. Okay, so now it's your turn. We've got 3 questions here. Pause the video, have a go at these, and when you're ready for the answers, then press play and you can check to see if you've got them correct. Okay, here we go. So this first question, this is a very typical question in the exam. It could be 4 marks, it might even be 5 or 6 marks. So we need to get the details. So we need to talk about diffraction. We need to talk about the distance travelled. So they meet in phase. Where they meet in phase, we get constructive interference. We get a bright fringe. Where we get 0.5 of a wavelength, or in fact 1.5, 2.5, 3.5. So we could write this as n plus 0.5 lambda. We get the waves meeting 180 degrees out of phase, so we get destructive interference, which is a dark fringe. So lots of detail required there. Question 2 is the basic calculation. So as always, write the formula, substitute the numbers, make sure you get the units correct. So very often they'll give you millimeters and centimeters. So the slit separation 1 millimeter, 1 10 to the minus 3, multiplied by the fringe separation 0.15 centimeters, divided by 100, divided by 2.4 meters. You would expect normally to get a value somewhere between 400 nanometers and 700 nanometers. Not necessarily, because this does work with UV and infrared and indeed any of the wavelengths in the electromagnetic spectrum. But generally speaking, we would expect to see visible lights being used in this. Also, we need to consider what would happen if we make certain changes. So very often the exam question might say, if you reduce the slit separation. Now this is a good idea. The reason why is because reducing the slit separation A would increase the fringe separation Y. And we can make reference to this formula here, because the slit to screen distance in part A doesn't change. The wavelength certainly doesn't change. So if I reduce A, if I make that smaller, in order for both sides to balance, I'd have to increase the delta Y, which is what happens. So your explanation could make reference to this formula here. So it's a good idea to keep A as small as possible, because that gives you a larger fringe separation, which is easier to measure. Similarly, if we increase the slit to screen distance, that is making capital D larger. Again, lambda's the same, A is the same. If I make D larger, I'd have to make the fringe separation Y larger in order for this formula still to make sense. And again, this is a good idea in practice to increase D to make the fringe separation as large as possible, to make it easier to measure. And we could also say to reduce the percentage uncertainty. Okay, so we have the fringe pattern for Young's fringes, which allows us to calculate lambda, but it's a little bit blurry and the gap between the fringes is quite small. So it's quite hard to measure, and there's quite a lot of error associated with it, so the percentage uncertainty is relatively large. A better way of measuring the value of the wavelength of light is to use a diffraction grating. So diffraction grating is a small device or component which has hundreds of slits, very, very closely packed, and we've just got a few shown here, 1, 2, 3, 4. What we have here is, rather than just 2 waves meeting in phase, and then 2 waves meeting in phase here, we have hundreds of waves meeting in phase. So what we end up is with a fringe pattern which is far brighter, so we have very bright dots. We also have an increased separation or fringe spacing between those. So it's a lot easier to see. it's a lot easier to measure, it reduces the error, it reduces the percentage uncertainty. Now we will talk about the derivation of this formula later on in this topic, but we can just accept this for now. N lambda is equal to d sine theta. So what do these terms mean? So lambda is obviously the wavelength of light, that's what we're trying to find. D is the slit separation, which is going to be a very small number. Lambda is the angle of deflection from the midpoint. So this is a top view of the fringe separation here. So the midpoint, the brightest dot in the middle, is referred to as n is equal to 0. So that's the 0th order. The dot on either side, so this one and this one, left and right, is the first order, n equals 1, n equals 1. The next dot is going to be the second order, n equals 2, n equals 2. So when we talk about which order of spectra are we talking about, it just means which dot are we referring to. Is it the first on the left, the second on the left, the first on the right, the second on the right? So the n just refers to which number we're talking to. And theta is this angle of deflection. So obviously theta is going to be 0 for the central fringe, and then the first fringe is going to be theta 1, the second fringe is going to be theta 2. So this is our standard question in the exam. Let's have a look at it. So we've got, we're trying to find the wavelength of light. The first order spectra, n equals 1, is given as an angle of 15, and we're told the diffraction grating spacing, so a really tiny number as we would expect. So part A, to calculate the wavelength, rearrange this formula, lambda equals d sine theta over n. We've got d, we know theta, divided by n, it's the first order, so just divide by 1, and we can calculate a value of theta. We could then also go on to find the angle for the second and the third order spectra, so that's the second dot and the third dot, either the left or the right. So in this case we need to make theta the subject, so we have to rearrange this, so it's going to be lambda n divided by d and then sine to the minus 1. So we already know lambda, we know d, that hasn't changed, but now n is the second dot, so n equals 2, and we get 31.2. We repeat the calculation with n equals 3 and we get 50.10. So we can do this for all the dots until we run out of dots, and we'll see that later on in the topic. The number of lines per millimetre, so we've got to be a little bit careful here. Confusion can set in here. The first thing to do is to realise that the number of lines per metre or per millimetre is the reciprocal of the separation in either metres or millimetres. So the number of lines is going to be 1 over d. But the best thing to do here is to convert the 2.28 10 to the minus 6 metres into millimetres at this point. So multiply by 1,000, 2.28 10 to the minus 3, and then find the reciprocal 1 over that, which comes out as 439 per millimetre, because the millimetres is on the bottom. So we've got 439 lines per millimetre. So as we said before, hundreds of lines, which is why we get this intense fringe brightness, because we have hundreds of rays all meeting constructively at the same point. Okay, so have a go at these two questions, pause the video, and then press play when you're ready to check your answers. So question 1, we need to make a reference to the fact that there's hundreds of slits closely spaced together. So we do get a fringe pattern, we get a greater spacing and a higher intensity. The benefit of this is it's easier to measure, but that probably won't get you full marks in the exam. We need to make reference to the fact it reduces the percentage uncertainty, and then we get a better or more precise value of the wavelength. Okay, question 2, very similar to the worked example. So we make lambda the subject, d sine theta over n. We're given d, we're given the angle 38.2, and we're told n is 2, so that's the second dot. We can put the numbers in the calculator, and we get our answer 6.9 nanometers. The number of lines per millimetre on the grating, very typical question. So we need to calculate 1 over d, but d in millimetres, not metres. And we'd expect hundreds, so 476 sounds about right. It might be 500, it might be 300, but we'd expect something like that. So as always, show your working and watch out for this metres and millimetres conversion. Okay, a very quick recap. So we need to be able to explain how a fringe pattern is created with Young's fringes. That was our first method. And then make the comparison with a diffraction grating and explain why that is better.